All right, hello everybody. Welcome to Y2K was a feature, accounting for time and software. My name is Brian Sewell. I am from Durham, North Carolina. If you need to reach me, my email is up there. I will post it again at the end of the talk. I am an engineer at AdWorks in Durham. I've been there for almost 3 years now. And if you are interested in learning a little bit more about what we do, we are hiring, so catch me in the hallway after the talk. So when I was researching topics for this, there were a handful of routes I could have gone, but I wanted to focus on some of the bugs that we've run into when dealing with time and software, because they're the ones that seem to bite us the most. And when I was doing my research, I came across this super helpful Wikipedia page that listed every single time-related programming bug, at least to most people's knowledge, and I came across Y2K. So who here knows what Y2K is? Okay, great. Who here was alive during Y2K? All right, I have to ask. All right, cool. I'm assuming 99% of you were born before 2000. All right, so for those who are unfamiliar with what Y2K is, it referred to the issue where we were storing years as 2 digits instead of 4, and the consequences of that when we would hit the year 2000. It was called the Millennium Bug, the year 2000 problem, or Y2K for short. And businesses and governments all around the world were funneling billions of dollars into trying to replace hardware and patch software, anything that could have been affected by Y2K, or anything that people could convince them that would be affected by Y2K. There'd be toasters that would have Y2K compliant stickers on them. So even though Y2K was the perfect anecdote for a talk about time and programming, my first thought was honestly, what a perfect buzzword to put in the title to get people to come and look at and watch my talk. So thanks for taking the bait, I really appreciate it. So despite Y2K almost always being referred to as a bug, I would argue that it wasn't a bug at all, and it was more of a design compromise. Right? The compromise was to store years as 2 digits instead of 4 to save space. Space was limited and expensive early on in computing, and this just sort of became the norm for how we stored years. And it stayed the norm for a very long time, all the way up until about 2000. No one could have really predicted that all the systems that were storing things as 2 digits for their year would still be in use by that time. So Y2K was just one of these examples of a design compromise that we are constantly making in software. How many times do we design like a temporary solution that we know is not bulletproof, but it will last long enough and we'll just fix it later, right? And we just assume that we are going to fix it ourselves, or somebody else will deal with the problems that we've put in there. So Y2K was sort of this accumulation of technical debt that snowballed at the end of the 90s. And as much as I would love to talk about Y2K in more depth, we're going to talk about how to avoid problems like Y2K, specifically storing time, parsing time, and presenting time. Now, there's a whole lot to unpack here. So I'm going to stick to some of the basics, or at least some of the most relevant topics, like time zones, daylight saving time, UTC, leap years, and formatting. So we'll start with this question. How does time affect you? More specifically, how does it affect your app or business? Not every app or business revolves around a key component of time. But almost everyone is going to be affected by it in some way. So maybe you send out marketing emails on a schedule, or maybe you have scheduled jobs, or maybe you're ingesting a third-party API and you're storing timestamps from that API in your database, or maybe you have your own API where you're transiting dates and times from your database for other people to ingest. Or maybe your business does have a key component of time. Maybe you facilitate online auctions like eBay, or you've got a fantasy football app with live online drafts. Or maybe you're an airline that has to let your customers check into your flight no sooner than 24 hours. Or maybe your app facilitates some sort of scheduling, like a calendar or HR software. So let's start with this first aspect, which is storing time, and it's the beefiest one. So aside from not storing years as 2 digits, what are some best practices that we can follow? Of course, this depends if you're storing a date or a timestamp or a duration, but there are some standard formats that we can lean on. And the most common one that you'll see is ISO 8601. This was a standard that was adopted in 1988 to help prevent ambiguous timestamps. or at least date formats, and it defines these acceptable ways to display dates and times. So an ISO 8601 formatted timestamp would look like this. You've got the very first part, which is the year. The second part is the month. The last part, or the third part, is the day. Then you have this T delimiter in between the date and the time. The time is in a 24-hour format, so 15 is 3 p.m. You've got your minutes, your seconds, and then the last little bit is this time zone offset. There are a few other formats that you'll see, and they're used for specific use cases. RFC 3339 is a stricter version of ISO 8601. It basically says you can't leave anything out. You have to include time in your timestamp. You can't just represent the date, and you can't convert it to midnight. I think the only optional thing you can add here are like milliseconds or fractional seconds. RFC 2822 defines the dates, or the way dates and times should look like in email headers. So once again, the most common one you'll probably see is ISO 8601. So let's talk about time zones, because I know you're all really excited about it. These can be extremely tricky and probably are the most common cause for some of the issues that we run into when dealing with time. But before we get into exactly why or how we should store time zones, let's talk about why time zones exist and like how they came about. So before time zones existed, we basically told time by where the sun was. And this wasn't that long ago. It was only like 135 years ago. There could be a 10-minute difference between cities that were not even 100 miles apart. And this was just because that was the standard. And it caused a lot of confusion. So this is a timetable that was published in 1857, listing about 100 important US cities that people would normally travel to by rail, and what the time was relative to when it was noon in Washington, D.C. And railroad passengers would have to use these timetables to adjust their clocks and watches whenever they would get to their destination. However, each railroad company used a different standard for telling time as well, and they would post their schedules using their standard. So the more rail companies that did this, the more confusion there was. In fact, it led to a couple of collisions where the train guards on different trains had completely different time. Even if it was 10 minutes off, they had no idea there was another train on that track, and it led to fatalities. So this became a bigger problem as more people traveled by rail. So in October of 1883, the railroad companies in the United States and Canada held a convention in Chicago and said, we've got to fix this problem. We need to get everybody on this standard way of telling time. And so they agreed that at the end of it, we would have these 4, 5-ish major time zones in North America. And this is kind of where time zones were born-ish. After that, we saw a large adoption all over the world. A lot more time zones started showing up. But today, we have 39 time zones, which doesn't seem super normal since there's 24 hours in a day. But we'll get to some of the weird ones. So like Australia is kind of odd. They have 4 time zones. One is off by 30 minutes, and the fourth one is way too small to highlight here. But it's off by 45 minutes instead of 30. Russia has gone through a whole lot of time zone changes in the last 10 years. From 2004 to 2010, they had 11 time zones. And then they reduced it to 9. And then in 2011, all of them shifted forward an hour. And then in 2014, they all shifted back an hour and added 2 more time zones again. And then the most recent change in 2016, just a couple parts of the country shifted forward an hour again. So this is where we are in Russia today. So China, they used to be split into 5 time zones, but they only have 1 now. So over summer, there are parts of Western China that don't see the sunset until after midnight. But this isn't a huge deal because like 95% of their population lives in the eastern half of the country. There have been numerous instances where countries have moved from one side of the international date line to the other. So they either skip over a day or relive the same day twice. They did this to align with their trading partners because there was a potential of them missing out on an entire workday. So it was an economic and political issue. In the US, we don't have time zones that match our state geographical borders perfectly. We have 14 states that are split between 2 time zones. Okay, so this seems like a whole lot of edge cases to keep track of. Like, how do we do this? Luckily, there's this thing called the TZ database, and it keeps track of all this historical information so that we don't have to worry about it. And it gets updated periodically. In fact, I think it was updated in July, the very beginning of July. This typically lives on your machine to interact with libraries and other languages. So how should we store a time zone? What's the proper way to get this into our database? Let's say we wanted to store a user's preference for their time zone. What's the best way to do this? So some languages and frameworks have defined their own like friendly names for these time zones, and you'll see these a lot, like Eastern Time. And these are usually meant for displaying purposes. They're not really meant for storage. Each time zone also has an abbreviation, EST, for Eastern Standard Time. They will also have an offset, and this is defined as the number of hours ahead or behind of Greenwich Mean Time. And then there's the identifier, the canonical name that is in the TZ database. So which of these should we use? Which one should we store in our database? Well, once again, the first one is usually pretty specific to the language or framework you're using. So because it's not a standard, we probably want to avoid this. The abbreviations aren't always the same for the same time zone either. They'll change, and we'll get into that in a bit. And the offsets could be ambiguous. Numerous time zones could have the same offset. So that leaves us with the TZ database name. This is probably your best bet for if you needed to store a time zone. It's unambiguous, and it is a standard used in almost every programming language. So back to that abbreviation, EST. It seems like a very attractive option, right? Developers are like, oh my God, an abbreviation, this seems so simple. But these will actually change. So EST, once again, stands for Eastern Standard Time, but it's only a time zone for 4 months out of the year. The other 8 months, it's Eastern Daylight Time. And that's because of this wonderful thing called daylight saving time. So other than messing up your sleep schedule or making you hungry an hour early before lunch in the fall, daylight saving time can really wreak havoc in your app if you're not accounting for it properly. So the first thing to note is not everyone observes daylight saving time. In fact, I think the majority of the population of the world doesn't observe daylight saving time. Remember how Australia had those weird time zones? Well, only parts of the country observe daylight saving time. So you get more time zones during only part of the year. The United States, Arizona, doesn't observe daylight saving time except for the Navajo Nation. Hawaii has never observed daylight saving time because they don't really need to. There are actually a handful of states that have passed bills or are currently trying to pass bills to permanently observe daylight saving time. So when that happens, buckle up. So not everyone who does observe daylight saving time starts and ends at the same time each year either. This varies by country as well. In the United States, we start on the second Sunday of March and we end on the first Sunday of November. And in the UK, they start on the last Sunday of March and end on the last Sunday in October. Because Australia is in the southern hemisphere, they start daylight saving time in October and end in April. And even the hour the changeover happens is different by country. So in the United States, when we start daylight savings time, we're losing an hour, right? And so we are skipping over an hour completely. That happens at 2 a.m. here. So we go from 1:59 Eastern Standard Time straight over to 3 a.m. Eastern Daylight Time. 2 a.m. Eastern Standard Time does not exist. In the UK, this happens at 1 a.m. instead of 2 a.m. They go from 12:59 Greenwich Mean Time to 2 a.m. British Summer Time. When daylight saving time ends, both the UK and the United States do this at 2 a.m., so they relive 1 a.m. twice. So there's plenty of edge cases that we have to deal with in daylight saving time, and luckily, it's all in the TZ database. All the historical changes and all the current up-to-date information, it lives there, and it, once again, gets updated periodically. So why do we care? Even with the help of the TZ database, time zones and daylight saving time is an added complexity that we need to be aware of. If you have emails or text messages that you're sending to your customers, maybe at like the close of business each day, are you sending those in their time zone or in your time zone? Because if you are on the East Coast and you want to send somebody an email at 8 a.m., everyone on the West Coast is going to get it at 5 a.m. Same for scheduled jobs. If you are calculating durations anywhere, like doing some manual date math, first of all, that's terrifying. Second of all, you might have to account for the daylight saving time changeover. It might mess up your durations. Imagine if somebody was using Runkeeper and they decided to go for a run during one of these changeovers, and then they opened their app and it said that they ran for negative 40 minutes or something like that. All right, so let's go back to this timestamp. This is this negative 0400 bit. It represents the time zone, but what is it relative to? So time zone offsets are defined relative to UTC. And UTC stands for Coordinated Universal Time. It was formally adopted in 1972, and if you're wondering what's up with that acronym, that's because the French abbreviation was TUC for their translation, and the English-speaking countries still used CUT, and so they just picked UTC because it was the same in every language. Yeah. It gets worse. So UTC is a standard to help regulate clocks around the world, and we define time zone offsets relative to UTC. So if we put all the time zones on a number line, 0 would be kind of in the middle. So during standard time, the Eastern time zone in the US is 5 hours behind, so minus 0500. And China is 8 hours ahead of UTC, so plus 0800. But during daylight saving time, Eastern time shifts forward an hour. So now the offset is minus 0400, and China's offset remains the same because they don't observe daylight saving time. But you can see this is how those offsets are ambiguous. Negative 0400 doesn't always mean Eastern Standard Time or Eastern Daylight Time. So to keep things simple, if you are storing a timestamp in your database, you should probably use UTC. You'll save yourself some headaches down the road, and you can convert it to whatever time zone you need upon retrieval. But storing it in UTC keeps it unambiguous. And the way we do this in ISO 8601 is we replace the offset with the letter Z. This represents the 0 offset from UTC. So there's another way to store timestamps that doesn't require us to keep track of the individual components, like the month or even the time zone, and that's this concept of Unix time. Unix time is defined as the number of seconds since January 1st, 1970, the Unix epoch or epoch, however you like to pronounce it, and it's essentially a relative point in time. So a Unix timestamp would look like this, if we converted today's date to a Unix timestamp at midnight, I guess. A lot of systems use these timestamps to store time. They'll use Unix timestamps, and they do so by storing them as signed 32-bit integers. If you don't know a lot of binary, neither do I. So I only know enough to put it up on this slide, so please just use the squint test here. If you represent a Unix timestamp as a signed 32-bit integer, it looks like this, a bunch of ones and zeros, right? Signed means that you are sacrificing a bit to represent whether or not it is positive or negative. This first bit is used to encode that, so 0 means positive, 1 means negative. The maximum positive integer that we can represent as a 32-bit signed integer looks like this. All ones except for that first one means it's positive. So if this was Unix time, what date would it represent? So you'll get January 19th, 2038, about 3 a.m. UTC. So what happens when we pass this date and time? So depending on the system, the conversion to daytime might just stay the same. Might think it's that date forever. Or it could roll over and think it's 1901 and start counting up from there, which could be a problem. Either way. This is known as the 2038 problem, and it's being sold as the next Y2K. We're actually closer to this date than we are to January 1st, 2000, so it's time to panic again. Maybe not yet. So there's already been some pretty high-profile instances of this issue. NASA launched a probe back in 2005 to inspect the interior of a comet, and it succeeded in its mission and was going off doing other missions, and they lost contact with it in August of 2013. And NASA reported that they lost contact with it because the onboard computer just kept rebooting over and over and over and over again. And they determined that the reason for it was similar to this exact same problem, dealing with time. They were tracking the runtime of the probe by the number of 10th seconds since January 1st, 2000, and they were storing that value as a 32-bit integer. And it rolled over the exact moment that the computer just started rebooting over and over and over again. The total cost of developing that probe was $330 million. So it was not it wasn't a minor bug. It was definitely a problem. And there was no way to fix it, right? It's in space. So you got to do this beforehand. This problem is not limited to tracking time either. If you're using MySQL or Postgres and you have a table that's approaching 2 billion rows, you probably could run into this issue. At AdWorks, we actually ran into it this month. We had a table that we were using for like audit logs, and we kept getting this honey badger saying that we were having like a duplicate entry for a primary key. And I saw this and I freaked out because I was in the middle of preparing this talk and this number had been haunting my nightmares. So yeah, the auto increment function in MySQL just kept trying to use that max value over and over and over again. So we kept getting this error. YouTube, they had to update their view count column to store their view count as 64 bits instead of 32 bits because back in 2014, Gangnam Style was about to hit the limit. And in fact, we've had many more YouTube videos exceed that limit since, but they never thought anybody would ever watch a video that many times. They have. All right, so if this is the max number we can represent as 32 bits, if we update our columns to be 64 bits, what's our new max number? Well, it's this. I don't know how to say it, but that's it. So if we convert this to a Unix timestamp, it gives us this date, which I think will be good. All right, so what if you're parsing time from an API or a user input? Obviously, you cannot control what format they send you, but most languages will give you some sort of a best guess date parser that you can use. So PHP has a string to time function. There's also a date parse function that will give you like an array of all the date components. All of Ruby's date and time classes will have a parse method, but they all kind of expect the string you're passing it in to be like ISO 8601-ish. Otherwise, it'll just raise an exception. There's a date util module in Python that has similar behavior. And native JavaScript can parse things into dates as well, and you can do it two ways. So you can pass a string as into the date object, and it will spit out a date object, or you can use the parse function, and it will spit out Unix time in milliseconds. And there are some oddities we'll want to be aware of when using JavaScript. So what date will we expect when we parse this? Looks ISO 8601, right? Everything should be great. So on my machine, since I have, well, I guess I'm in Pittsburgh, and so it thinks I'm in Eastern Standard Time, Eastern Daylight Time, it actually converts it to my local time. So for whatever reason, it parsed it as if it were UTC, and then spit out 4 hours before midnight, 8 p.m. yesterday, which is a little odd. So if we add in the time, suddenly it thinks that it's actually local time and it will give me local time. So I don't know why. Just be careful when parsing dates and times with JavaScript because you might get something you don't expect. What if we parse the exact same date but in this format? We can expect the same thing, right? Nope. For whatever reason, this format parses as midnight in your local time. I don't know why. I think it has something to do with the ISO 8601 format it might be expecting. But yeah, it's, once again, just be on the lookout for stuff like this with JavaScript. And you will need to parse dates like this every once in a while. A lot of people store and display their dates with the day first and the month second. So your best guess date parsers are just not going to work here because they're probably expecting a different format. So in order to avoid these kinds of ambiguities, most languages will also give you another method where you can define the format that you were expecting to see. Like Ruby and Python, they both have one. Stirp time, I think that's how I say it. Most of these will let you pass in that format as like tokens of whatever part of the date it is. So like, what is it, D for the day and M for the month, Y for the year. PHP has a stirp time method too, but I think the more preferred method is create from format. I have not used PHP in 7 years, so don't quote me on that. I just used a GitHub search, and apparently more people are using that, which might not be a great measurement of whether or not it's right. So, disclaimer. JavaScript does not have a function to do this out of the box, so you'll have to use a library like day.js or moment.js. All right, so let's say we have a form submission or an API response, and we wanted to store the starts at or ends at date in our database. We'll have to convert these times or these strings into dates. Now, since these timestamps are actually already kind of formatted like ISO 8601, our best guess date parsers are probably going to be just fine here. And same if they use Unix Time. But if they're sending it to you in numerous pieces, you'll have to do some more work. This might be more common if you're using like a date picker in an HTML form. What if you need to parse natural language, right? Some languages will have plugins to help with this. Like, you'll still need to clear up some ambiguities, like noon in which time zone, for instance. Like the chronic Ruby gem, it's been around for a while and is well maintained. It supports full text parsing like this. There's a date parser library in Python. There's also some good natural language processing APIs out there if your language doesn't support it, or if there's not already an existing library. All right, so once you have a date object, most languages will let you extract information from that date object, like what day of the week it is, or what's the name of the day, or what week in the year it is. JavaScript has a lot of these functions built in, surprisingly. But there's one you do not want to use, and that's getYear for Y2K purposes. It returns the year as the number of years minus 1900. It was deprecated back in 1997 in favor of getFullYear, which does return the year in 4 digits, but not everyone ran and updated all their code, so getYear is actually still in use a lot. And it's in the ECMAScript standard for backwards compatibility purposes, but they just recommend you not use it anymore. All right, so why do we care, right? So things to keep in mind when you're parsing dates. If you are parsing dates from a third-party API, check to see what format they're sending it to. And if they aren't sending it to you in like ISO 8601, use one of those parsing methods where you can accommodate that specific format. There is really no one-size-fits-all method here. You're just going to have to be vigilant. Leap years, probably the last thing you're worrying about, but they do have some rules we need to be aware of. So how do you determine if a year is a leap year? The rules are if the year is divisible by 4 and it's not divisible by 100, unless it's divisible by 400. I'm glad I got laughs out of that because I had no idea this was a thing. I felt really weird. But so this means that 1600 and 2000 were leap years, but all the other centennial years weren't. So 2400 is our next centennial leap year. Yeah, once again, I had no idea until I had to research it for this. I asked my entire family, I was like, hey, who knows how leap years work? And almost everyone was like, I don't know, every 4 years? I was like, cool, I'm putting it into the talk. All right, so if we wanted to use or write a function to check this logic, we could do so, or we could lean on some of the date libraries our languages might already have. Native JavaScript does not have one. So once again, you'll have to write something like this. This is actually straight out of the moment.js library. And you can check a leap year in a little bit more of a bizarre way in JavaScript. And so you can initialize this date object, and you can pass in for the date or the day field more days than are actually in that month, and it will give you like whatever day it is. So like the 32nd day in December is really January 1st of the next year. This works, by the way. I don't know why. So 11 here represents December because it's a zero-based system. So we could write a function using that, right? We could just pass in a year and check to see if the date is in the month of February, and if it is, it's a leap year. This is actually a more common method used in spreadsheets, where you don't have a whole lot of functions to manipulate dates. In the 80s and 90s, IBM Lotus users could determine if a leap year was a leap year by doing the same type of calculation. And they would enter the 29th of February and say, hey, is the month equal to 3? Then it's not a leap year. Or if the month is equal to 2, it is. But a bug made 1900 actually return true. So Excel decided that they would support this functionality for backwards compatibility, and it made its way into the OpenOffice XML standard, and it's still there. So if you ever develop anything supporting that, you have to make 1900 a leap year. All right, so why do we care? Leap years are so predictable, like why do we need to worry about them? Well, maybe you're making some sort of payroll software, right? And you're sending out checks at the end of the month. Sending out a check a day early, not a big deal. Day late, probably a big deal. Maybe you need to program in some subscription billing, or maybe you have a calendar app or something that schedules events in general. Or you'd want to validate that the 29th of February is an actual date in whatever year they're trying to create an event. And then anywhere you're dividing by 365, I don't know why I thought of this, but I think we've done this numerous times in our code base. So if you just search for 365 or maybe like, /365, you might be surprised. All right, so the last but not least, or not the most important part, but one of the last little bit is presenting time. How are we going to use all this information about how we want to store time and parse time and use it to be good shepherds of like presenting time to everybody? So if you need to transit time via an API, like a timestamp, your best bet is to use ISO 8601 or Unix Time. If you're having a hard time choosing a format, don't feel bad. Stripe's API uses Unix Time. Facebook's API uses ISO 8601 with a time zone offset for local time. Twitter uses the JavaScript full text format. GitHub uses ISO 8601 in UTC. And Google Drive formats their timestamps using RFC 3339 with milliseconds. So once again, just pick one of the standards and be consistent. And be aware of time zones as well. If you are sending a timestamp out and the time zone is important, send the timestamp as UTC and the time zone along as its actual identifier from the TZ database. This way the users can convert it to whatever local time they need to or they want to. If you are displaying a time zone in a UI, you've got a few more options. You can send it as the abbreviation. You can show it as the offset. You can show it as the friendly name. It's really up to you. If you're displaying start and end times in your app and the start time has a different time zone than the end time, your UI should probably reflect that. This is a Southwest flight itinerary I had last week, and I was surprised even in the app and the email, at a glance, I'm like, oh cool, my flight's almost 25 minutes long. Even though it shows on the right-hand side that it's an hour and 25 minutes. There's no time zone information here, so at a glance it'd kind of be weird. Especially if you're traveling from the West Coast all the way to the East Coast. It'd be a very long-looking flight. You'd be like, oh my God, that's a 10-hour flight from San Francisco to Raleigh. So if you're displaying a date or time on a web page, you can use this time tag, and this will help make it machine readable. So for screen readers or for search engines, and you can add a date time attribute as well if you need to represent some sort of relative date or something that's not a standard. For everything else you do with presenting time, just be consistent, right? Just pick a format that is relevant to whatever you're using it for and adopt a standard where possible. All right, so to wrap things up, let's list a few things that we can use to be a little bit more diligent when dealing with time. All right, first we can start by adopting some standards. ISO 8601 is a widely used standard. It's very simple, and you're probably even using it right now without knowing it. Try to store timestamps in UTC rather than in local time. Store and present time zones using the name in the TZ database instead of maybe the friendly name or the offset. Present time zones when necessary, like that flight itinerary example. Start storing Unix timestamps as 64 bits soonish. Don't wait till 2037. Be aware of leap years because they could throw a wrench in the mix. And we've got one coming up. 2020 is a leap year. So. And here's some things we just need to be aware of, like how the world deals with time. Not everyone observes daylight saving time, and those who do don't do so at the same date or time. And the daylight saving time rules will change. In fact, I think the United States, they changed them back in 2007, and they're bound to change in the next 10 years. Time zones change as well. The offsets with respect to UTC are ambiguous to the time zones, like -0400 is not always the same for the East Coast. And not everyone uses the same format for dates and times. So things to be aware of. So thank you all so much for coming. I really do appreciate you finishing the week here. If you have any fun Y2K stories that you want to tell me about, I will be out here on my way to the keynote. And also, one last thank you I want to give out is for my wife. This last 2 months, I've basically been coming home every day and sitting in my office for numerous hours trying to prep for this. And if there are any speakers in here, you know how much time goes into this. So thank you, Nikki, so much for taking care of our daughter basically single-handed the last 2 months. I love you very much. And honestly, this would not have happened if it wasn't for her. So thank you, everybody. Enjoy the final keynote and come talk to me afterwards if you want to. All right. Great work. Thanks, man.